So previously we have talked about examples of subgroups, and we have said that we define the center and said that center is a subgroup of the group, and we define the centralizer, and then we said that centralizer of any element is a subgroup. Now we will do some exercises about this chapter. So we start with number one, which is prove that in any group an element and its inverse have the same order. And we provide the solution. The solution will be, suppose that order of an element is equal to some n, and order of its inverse is equal to some k. Then order of a inverse power n is going to be a power n minus 1, which is going to be minus e power minus 1 equals to e. Okay, so k should be less than or equal to n. Now reverse the roles actually, not roles of a and a inverse to obtain n is less than or equal to k. Okay, and this then hence n is k. Now the infinite case follows from the finite case. Okay, perfect. Then we say that determine all elements of finite order in number 2 is determine all elements of finite order n are star non-zero real numbers, which is the group of non-zero real numbers under multiplication. So we can write that in this sense. Now solution. So let's say if n is a positive number, n is a positive integer, the real solutions of of x power n is equals to 1 are 1 when n is odd, and plus minus 1 when n is even. So the only elements of finite order in the group or star under multiplication or plus minus 1. Okay, perfect. Then we say suppose that A is a group element and A power 6 is E. What are the possibilities for the order of A? What are the possibilities for order of A? Provide reasons for your answer. Now, solution. Now, the possibilities are 1, 2, 3, and 6. 5 is not possible for A power. 5 is not possible for if A power 5 is E, then E is going to be equal to A power 6, which is going to be equal to A into A power 5, which is going to be equal to A. 4 is not possible. 4 is not possible for if A power 4 is E, then E is going to be A power 6 equals to A square A power 4, which is going to be A square. But all other elements like 1, 2, 3, and 6 is if A square is E, then E is going to be A power 6, which is going to be A square into A square into A square, which is going to be E again. Similarly, if A cube is E, then E is going to be A power 6, which is going to be A cube into A cube, which is E. Answer. Okay, perfect. Then number, let's say we have number 4, which is if A is the group element, if A is in G in any group, and A has infinite order prove that a power m is not equal to a power n when m is not equal to solution. So we suppose that m is less than n and a power m is a power n. On the contrary, then we say that e is going to be a power n into a power minus m, which is going to be a power n minus m. Now this this contradicts the assumption that A has infinite order, because this one it's going to have finite order. Now number 5 says we show that if A is a group element, is an element of a group, so show that if A is an element of the group, then order of A is less than or equal to order of G. Now to show that, we say that, say if A A has infinite order, then we have E, A square, and so on are all distinct and belongs to G. G. So G is infinite. Now, if A order of A is n, then A power I is some A power J, equal to some A power J, where 0 is I is less than J and they are between 0 and n, and it implies that A power I minus J is E, which is a contradiction, is a contradiction. Thus, contradiction in a sense that A has a finite order now. So, thus, E A square A power n minus 1 are all distinct and belongs to G. So, G has at least n elements. G has at least an elements. Number 6 says that show that U of 14 is generated by 3 and 5. Hence, U of 14 is cyclic. Now, is U of 14 generated by its element 11? Okay, now solution. So let's see, 3 generates the elements under modulo 14, 3, 3 square, 3 cube, 3 power 4, 3 power 5, 3 power 6, and these are going to be under mod 14, 3, 9, 13, 11, 5, and 1. And this is nothing but U of 14 itself. Similarly, I can write something for 5, which is going to be 5, 5 square, 5 cube, 5 power 4, 5 power 5, and 5 power 6. And that is going to be 5, 11, 13, 9, 3, 1 is also equal to U of 14. Now remember what when we are doing, let's say we have 5 square. As an example, we have 5 square. 5 square is equal to 25. Now 25 under mod 14 is going to be what? 11. That's why 5 square is 11. And similarly, if you have 3 cube, which is 27, that is going to be under mod 14 equals to 13. Okay. Now let's see what 11 can generate. 11 is going to be equals to 11 itself, 9, and 1, which is not actually the U14. Okay, perfect. So one last, which is 7, says that show that U of 20 is not generated by any element k for any k and U of 20, means U of 20 is not cyclic. So we need to show that. So let's consider that since order of U of 20 is 8. Now for U of 20 be equal to be generated by some k for some k, it must be the case that order of k is 8. 1 second. So order of k, in that case, order of k must be 8. But and the elements inside U20 have these orders. Let 1 have order 1, 3 have order 4, 7 have order 4, 9 have order 2, 11 have order 2, 13 have order 4, 17 have order 4, and 19 have order 2. So the maximum order of any element is 4. So the maximum order of any element 4. So there's no element of order 8 inside U20, so it can't generate. So there U20 have no generator. And that's it for this lecture. Thank you so much.